This focused exercise is called Simulating a Discrete Random Variable Probability Distribution Using Cubes. So what my students did is choose a cube from a container of colored cubes. We're going to create a table and list all colors and the count for each color. So this is an experiment that has already happened. So I just wanted to give you an example of a discrete random variable that you could relate to. And you could conduct this experiment on your own and add your data to this existing data. So we're going to start out by listing the colors of the cubes that my students have already drawn. And those colors were blue, black, pink, yellow, and orange. 4 students chose the blue block. 1 student chose black, 1 student chose pink, 3 students chose the yellow block, and 1 student chose the orange block. So now that we know the count, that total is 10. Since we're going to calculate mu and sigma, which represent the mean and the standard deviation, we will need to fill in the other columns for our table. So the first column for x squared, we're going to take 4 blue blocks. 4 squared would make 16. 1 squared would make 1. Again, 1 squared makes 1. 3 squared makes 9. And again, 1 squared would make 1. Our probability of x means that 4 out of 10 blocks were blue. So 4 divided by 10 would give us 0.4. 1 out of 10, or 1/10, is 0.1. Again, we have 0.1. And for the last one is again 0.1. And for the yellow blocks, there were 3 out of 10 that were yellow. So that is the probability 0.3. You should check out the sum of your probabilities, and remember it should equal 1. 0.4 plus 0.1 plus 0.1 plus 0.3 plus 0.1 is 1. You should not have more than 1 or less than 1. The next column is our x value multiplied by the probability. So this means we have 4 times 0.4, which is 1.6. And then 1 times 0.1 gives us 0.1. Again, 1 times 0.1 gives us 0.1. 3 times 0.3 would give us 0.9, and 1 times 0.1 gives us 0.1. We need to find the sum of this column, so adding up all of these values, we get 2.8. And for the last column in the table, we're taking our x squared value and multiplying by the probability of x. So x squared is 16, and that's multiplied by 0.4. That gives us 6.4. Next, we have 1 multiplied by the probability of 0.1, which gives us 0.1. Then we have 1 times 0.1 again. Then we have 9 times 0.3. That would be 2.7. And finally, 1 times 0.1 again is 0.1. So we need to find the sum for this column as well. So the sum is 9.4. Now that our table is complete, we can look at question 5 to calculate mu, which represents the mean. And that would be the sum of the x, px column. We've already found that sum, and that would be 2.8. So 2.8 is the mean. We find the standard deviation by taking the square root of the sum of the x squared px column and subtracting mu squared. We found that mu is 2.8, so mu squared must be 2.8 quantity squared, which is 7.84. So we can use the information from our table to make substitutions into this formula. Standard deviation is equal to the square root of the sum of x squared px, which we know is 9.4, and we'll be subtracting mu squared, which is 7.84. So on your calculator, depending on which type of calculator you have, you might need to do the subtraction first and then take the square root, or you might need to choose square root function first and then do the subtraction. Either way, the answer comes out to about 1.25. So our standard deviation is 1.25, and our mean is 2.8. The final part of this focused exercise is to determine which colors fall within 2 standard deviations of the mean. We're going to compare the results to Chebyshev's rule and the empirical rule. So what we'll need to do next is draw the distribution curve, labeling the mean and the standard deviations for within 3 standard deviations of each side of that mean. So we'll start with our line, and then I'll draw a smooth curve over this line. And I'll draw a bar representing the mean and each standard deviation. Our mean is 2.8, and with a standard deviation of 1.25, I'm going to add that to 2.8 to get 4.25. Add another 1.25 and we'll get 5.3. And finally add another 1.25 to get 6.55. Starting again at the mean, going to the left means I'm subtracting a standard deviation. So 2.8 minus 1.25 gives us 1.55. Subtracting 1.25 again, I'll have 0.3. And subtracting another 1.25 gives us a negative 0.95. So these are the x values that we find for under our distribution curve. What we're looking for is within 2 standard deviations of the mean. We're going to compare our results to Chebyshev's rule and the empirical rule. So let's shade in within 2 standard deviations of the mean. That means this area under the curve. So the interval we're concerned with between 2 standard deviations of the mean would be from 0.3 to 5.3. Now that we have the correct interval for our x values, we can go back to the table and look at the column for count. And we're going to look for any counts that fall between 0.3 and 5.3. So 4 is a number that falls between 0.3 and 5.3. 1 falls in the interval. There's 1 again. 3 is a number between 0.3 and 5.3, and 1 is also a number in that interval. So every one of our counts, or x values, does fit in this interval from our minimum of 0.3 to a maximum of 5.3 for 2 standard deviations. So we'll look at our data in comparison to Chebyshev's rule and the empirical rule. Within 2 standard deviations, 100% of our data falls in the interval of 0.3 to 5.3. Chebyshev's rule says that 75% of the data should fall within 2 standard deviations, while the empirical rule says that 95% of the data should fall within 2 standard deviations. So if 100% of our data falls within 2 standard deviations, it meets or exceeds Chebyshev's requirement, and it meets or exceeds the empirical rule. If we look 3 standard deviations beyond the mean, we'll still have 100% of our data. Chebyshev's rule says that 8/9 or 88.89% of the data should fall within 3 standard deviations, and the empirical rule states that 99.7% of the data should fall there. Well, again, 100% exceeds both of these. So how do you know which rule is the better predictor? You would choose the rule that is closer to your actual data. So 95 and 97%, it looks like the empirical rule is closer to 100% than Chebyshev's percentages. So the empirical rule is a better predictor of the probability.